We all know what a computer program is. It's that lifeless executable icon sitting quietly on your hard drive, waiting for you to double-click it. The program itself is a lifeless thing. It just sits there on the disk, a bunch of instructions, and maybe some static data, waiting to spring into action. But what happens the exact millisecond you open it? In the world of operating systems, a magical transformation takes place. It is the operating system that takes these bytes and gets them running, transforming the program into something useful. That lifeless file springs into action and transforms into a completely dynamic entity. The process, informally, a process simply as a running program. But behind that simple definition lies a massive engineering challenge. Look at your machine right now. It turns out that one often wants to run more than one program at once. For example, consider your desktop or laptop where you might like to run a web browser, mail program, a game, a music player, and so forth. In fact, a typical system may be seemingly running tens or even hundreds of processes at the same time. Doing so makes the system easy to use, as one never need be concerned with whether a CPU is available. One simply runs programs. Hence our challenge, how to provide the illusion of many CPUs? Although there are only a few physical CPUs available, how can the OS provide the illusion of a nearly endless supply of said CPUs? The OS creates this illusion by virtualizing the CPU. By running one process, then stopping it and running another, and so forth, the OS can promote the illusion that many virtual CPUs exist, when in fact there is a one physical CPU, or a few. This basic technique, known as time sharing of the CPU, allows users to run as many concurrent processes as they would like. The potential cost is performance, as each will run more slowly if the CPUs must be shared. Time sharing is a basic technique used by an OS to share a resource. By allowing the resource to be used for a little while by one entity, and then a little while by another, and so forth, the resource in question can be shared by many. The counterpart of time sharing is space sharing, where a resource is divided in space among those who wish to use it, like disk space. To implement virtualization of the CPU, and to implement it well, the OS will need both some low-level machinery and some high-level intelligence. We call the low-level machinery mechanisms. Mechanisms are low-level methods or protocols that implement a needed piece of functionality. For example, we'll learn how to implement a context switch, which gives the OS the ability to stop running one program and start running another on a given CPU. This time-sharing mechanism is employed by all modern OSs. On top of these mechanisms resides some of the intelligence in the OS, in the form of policies. Policies are algorithms for making some kind of decision within the OS. In many operating systems, a common design paradigm is to separate high-level policies from low-level mechanisms. You can think of the mechanism as providing the answer to a how question about a system. For example, how does an operating system perform a context switch? The policy provides the answer to a which question. For example, given a number of possible programs to run on a CPU, which program should the OS run right now? A scheduling policy in the OS will make this decision, likely using historical information, workload knowledge, and performance metrics to make its decision. Separating the two allows one easily to change policies without having to rethink the mechanism, and is thus a form of modularity, a general software design principle. At any instant in time, we can summarize a process by taking an inventory of the different pieces of the system it accesses or affects during the course of its execution. To understand what constitutes a process, we thus have to understand its machine state, what a program can read or update when it is running. One obvious component of machine state that comprises a process is its memory. Instructions lie in memory. The data that the running program reads and writes sits in memory as well. Thus, the memory that the process can address, called its address space, is part of the process. Also part of the process's machine state are registers. Many instructions explicitly read or update registers, and thus clearly they are important to the execution of the process. Note that there are some particularly special registers that form part of this machine state. For example, the program counter, sometimes called the instruction pointer, tells us which instruction of the program will execute next. Similarly, a stack pointer and associated frame pointer are used to manage the stack for function parameters, local variables, and return addresses. Finally, programs often access persistent storage devices too. Such I/O information might include a list of the files the process currently has open. Though we defer discussion of a real process API until later, any modern operating system must provide key interfaces. First, create. An operating system must include some method to create new processes, invoked when you type a command or double-click an icon. Second, destroy. Systems provide an interface to destroy processes forcefully to halt a runaway process. Third, wait. An interface to wait for a process to stop running. Fourth, miscellaneous control. Methods to suspend a process and then resume it. And fifth, status. Interfaces to get status information about a process, such as how long it has run for or what state it is in. Let us unmask the mystery of how process creation actually works. The first thing that the OS must do to run a program is to load its code and any static data into memory, into the address space of the process. Programs initially reside on disk or flash-based SDs in some kind of executable format. Thus, loading requires the OS to read those from disk and place them in memory. In early operating systems, the loading process is done eagerly, all at once before running the program. Modern OSs perform the process lazily, by loading pieces of code or data only as they are needed during program execution using paging and swapping. Once the code and static data are loaded into memory, some memory must be allocated for the program's runtime stack. C programs use the stack for local variables, function parameters, and return addresses. The OS allocates this memory, gives it to the process, and initializes it with arguments like args and the argv array. The OS will also likely allocate some memory for the program's heap, used for explicitly requested dynamically allocated data via malloc and free. The heap starts small and grows as the program requests more memory to handle data structures like linked lists, hash tables, and trees. The OS will also do some other initialization tasks, particularly as related to input-output. For example, in Unix systems, each process by default has 3 open file descriptors for standard input, output, and error. These descriptors let programs easily read input from the terminal and print output to the screen. By loading the code, initializing the stack and heap, and setting up I/O, the OS has set the stage. It has one last task: to start the program running at its entry point, namely main. By jumping to the main routine, the OS transfers control of the CPU to the newly created process and execution begins. Let us talk about the different states a process can be in at a given time. In a simplified view, a process can be in one of 3 states. In the running state, a process is running on a processor, meaning it is executing instructions. Ready. In the ready state, a process is ready to run for some reason the OS has chosen not to run it at this given moment. Blocked. In the blocked state, a process has performed some kind of operation that makes it not ready to run until some other event takes place, such as when a process initiates an I/O request to a disk. A process can be moved between the ready and running states at the discretion of the OS. Being moved from ready to running means the process has been scheduled. Being moved from running to ready means it has been descheduled. Once a process has become blocked by initiating an I/O operation, the OS keeps it as such until an event occurs, like I/O completion, moving it back to the ready state. Imagine 2 processes running. If process 0 initiates an I/O and becomes blocked, the OS recognizes it is not using the CPU and starts running process 1. Doing so improves resource utilization by keeping the CPU busy while the other process waits. The OS is a program, and like any program, it has some key data structures that track various relevant pieces of information. To track the state of each process, the OS keeps a process list, also called the task list. Individual structures that store information about a process are known as a process control block, or PCB, which is a fancy way of talking about a C structure containing process data. This includes a register context which will hold, for a stop process, the contents of its registers, so the OS can subsequently restore them and perform a context switch to resume running. Beyond running, ready, and blocked, there are other states tracked in the PCB structure. There is an initial state when a process is being created, and a final state where it has exited but has not yet been cleaned up, known in Unix-based systems as the zombie state. This final state is useful as it allows the parent process to examine the return code and see if the child executed successfully. When finished, the parent makes one final call to wait, indicating to the OS that it can finally clean up any remaining data structures. By combining these low-level mechanisms and higher-level scheduling policies, the operating system successfully virtualizes the CPU.